So this is a joint work with Itai, Arieli, and Manuel Mueller-Frank. Okay, so what social learning is about? So social learning forms an important part of social interaction, and in particular, what what the social learning tries to understand is how how agents learn from each other. So kind of classic standard model in observational learning is that agents initially observe some private information. Then agents repeatedly make decisions, and they observe each other choices observe the choices of their peers. And the questions that typically social learning literature addresses are the following. Do individuals end up doing the same thing? And do individuals end up doing the right thing? Okay, these are the type of questions that are typically asked. Now let me repeat the same slide, but slightly more formal and more specific. So a canonical setting of social learning is the following. So agents are located in a directed graph. Agents receive some initial information, which is captured by conditionally IID private signal about an unknown state. In this talk, I will talk about binary states. Okay, so there is an unknown binary state, and they form their initial belief based on their private signals. Okay. In each period, agent should choose a binary action, okay, which you may think of it as, let's say, that if we are talking about some product, if we don't know if it's good or bad, whether to adapt this product or not, or if we think of guessing what the state is to guess that the state is 0 or to guess that the state is 1. So every player chooses a binary action based on his current belief and updates his belief. And the way, after he observed the actions of his neighbors. I want to emphasize the difference of this talk from, I think, the previous two. Essentially, the main issue is that here players, they learn from actions of the others rather than from the beliefs of the others. They do not observe beliefs in this setting. They just observe what the other players did. Okay? This is the main distinction. So I didn't tell you what does it mean to choose a binary action based on current belief and what is updating, how we do this updating. So I want you to have in mind that in order to specify a dynamic, we should tell how what is the action choice based on beliefs and what is the belief updating rule. Okay? What are the desirable properties that we want in learning? So agreement, which means players essentially do the same thing, is that from some time on, remember we have just two actions, we want that from some time on, players will play the same action. Learning will mean that this displayed action will be also the correct action. Okay, remember the states are binary and the actions are binary. So learning will mean that they, from some time on, if the state is 1, they all will play 1. If the state is 0, they all will play 0. Obviously, it is impossible to achieve in small networks learning with probability 1, right? Because even if we gather all the information of all the agents, it still doesn't have a probability of 1 of success, right? We want some law of large numbers. So we want that at least, so we focus on the notion of asymptotic learning, asymptotic with respect to the network size. Okay, we want that the probability of learning will approach as 1 as the size of the network grows. Okay, this is the desirable property that we will focus on. Okay, so this model has been studied in both in Bayesian and in non-Bayesian settings. Let me first say what is known. So in a Bayesian setting, choice action is just a best reply. Okay, so let's say, for instance, that your utility is 1 if you guess correctly and 0 if you guess wrong. Then if your current belief is above half, you play 1. If it's below half, you play 0. Okay, very simple. And belief updating rules, it can be written in 2 words. It's Bayesian aggregation. You do the Bayesian aggregation, and so this model has been studied. This type of questions of do players learn, do they learn the correct thing, and etc. has been studied in paper by Mossel, Slay, and Tammuz. And they characterize conditions on the network that guarantee asymptotic learning. For the purposes of this talk, I just want you to emphasize the fact that they also give examples of large learning, of large networks where essentially asymptotic learning fails. Okay, for this talk, this will be important. And another issue that I want to mention about Bayesian learning, a recent result by Hasla, Jababai, Mossel, and Rayman states that essentially shows that Bayesian learning is very complicated object. I think the fact that conceptually it is very complicated object, people realized at the very beginning when they started working on these things, but recently it also has a computational evidence. It is p-space hard in very natural settings to apply Bayesian learning. Okay, this motivates the question of non-Bayesian. Okay, so can players learn by applying some simple heuristic? So the non-Bayesian setting in social learning has been addressed mainly in the context of continuum actions, which correspond to the case where you reveal your belief and not play a binary action. Okay, and there is a long list of papers, and there are others that talk about non-Bayesian learning in the context of learning from beliefs and not learning from actions. And this one is just the one that you saw a moment ago, and Segev mentioned also these other results. And another case where it was studied is in some very extremely simple dynamics, as majority dynamic, or for instance, the voter model, where essentially you pick a neighbor at random and mimic his action. This kind of extremely simple dynamics, it also has been analyzed. And obviously, these dynamics are too simple to achieve learning. Okay, and so the bottom line from at least from this literature, from the Bayesian and from the non-Bayesian, is that strong assumptions on the network are needed to guarantee asymptotic learning in the case in Bayesian or non-Bayesian case, in case where you just learn from actions rather than from beliefs. Okay, and our main contribution today, what I want to present you is we propose a simple non-Bayesian learning rule that is based on well-established kind of behavioral biases. This is the title of the talk, probability matching, and you will see some other behavioral biases along this talk. So, this simple dynamic will achieve asymptotic learning in all networks. Okay, for all networks, we will have asymptotic learning. This is what I want to present you today. The way I will present it, it will be in steps, and along the way, we propose a simple analog of the DeGroot dynamic in a binary action environment. And this dynamic will achieve agreement, not learning. Okay, players from some time on will play the same action, but not necessarily the correct one. Okay, so I just remind you that, let me say maybe what the DeGroot dynamic is. The DeGroot dynamic is very simple dynamic that every day averages the numbers of the opponents. And if everyone applies it, then essentially it leads to a consensus on some weighted average of the initial numbers. Okay, and so these numbers typically in many cases can correspond to some belief or an unknown continuum. If the state is unknown and you have some noisy signal, then essentially this is exactly what Jackson and Golomb demonstrated. So the DeGroot dynamic achieves consensus, but in a case where reports are real numbers. Okay, so what I will show is kind of natural dynamic that essentially achieves consensus, and we propose a simple dynamic that achieves asymptotic learning in vanishing influence networks, okay? Which is exactly, this provides an analog of all these papers that show existence of learning in vanishing influence dynamics, but we do it again in a binary action environment, okay? So let's start, so what is the first dynamic that I want to present is, I call it epsilon DeGroot. So I should specify you how the action, what is the action choice as well, and what is the belief updating. Let me start with the belief updating. So the way players update their belief, okay, they assign a probability 1 minus epsilon to their previous belief. This corresponds to kind of interior behavior of players. They assign more weight to themselves than to the others, and this is also kind of well observed in behavioral economics. And the probability epsilon to the weighted average of their neighbors. Okay, so and the Wij is that I should think of it as the way agent I influences me. Okay, that's so these are numbers that sum up to 1. So everyone averages somehow the opinions of his yes. Weights are fixed. Weights are fixed. And the action choice is, and now I should tell you what is how we do the action, how we choose the action given a belief. And here is the new idea that essentially allows, I think this is the key point that allows us to have all these positive results, is the fact that players do not choose their action deterministically given their belief, but they randomize it. Okay, and I think this is the main tool that allows us to have positive results, and in fact very positive in this context. And this is the fact that players are playing mixed strategies. Okay, so if my belief is BIT, then I'm playing. If my current belief is BI, I play action 1 with probability BI. Okay, so I'm playing, and with the remaining probability, I'm playing the same. So a proposition that this epsilon DeGroot dynamic essentially achieves an agreement always with probability 1. And if we want to understand, moreover, we know to say with which probability it will achieve a consensus on 1 and in which probability it will achieve a consensus of 0. So the probability of consensus of 1 is this number, where μi is the measure of centrality, and B0 is the initial beliefs that they received from their signal. And as you can see, this number is bounded between 0 and 1, and it does not achieve asymptotic learning, because with positive probability, it will fail. Okay, so this dynamic is not good enough. But if we apply to it some notion of extremization of opinions, that that player somehow extremize in this case, it's extremization of action. Instead of playing exactly the probability matching, what you are doing is, if your belief is here, you assign to it a probability slightly below the diagonal. If you are here, you assign to it probability slightly above the diagonal. Okay, so the theorem states that there exists a sufficiently small pair, epsilon and delta, such that the epsilon DeGroot, this extremized dynamic, achieves learning in all vanishing influence networks. Okay, and now finally to the last step, we want essentially something that works not only for vanishing influence networks, but for all networks. And here comes the idea that essentially in the initial state, you can update your way. So the idea is players can easily modify every network to a vanishing influence one. How they can do it? They can just modify the way that player I assigns to player J to multiply it by their current measure of centrality. And this will create a new network with new measures of centrality. And it is easy to show that the measure of centrality of this network is in fact uniform. And in particular, it says that this is how you just need to do it in the very initial stage. Okay, the very initial stage, instead of assigning some probability wij, you multiply it by your measure of centrality. And a corollary from that is that this dynamic achieves asymptotic learning for all networks. Okay. So, how many? 2 minutes? 2 more minutes. So let's talk 2 minutes about very broad idea of the proofs of these theorems. So let's start with the first proposition that says that the DeGroot dynamic essentially achieves agreement. Remember that my opinion is never 0 and 1. It always will be something else. Nevertheless, I defined agreement as if from some time on, players play some action with forever. Okay, so the way we can prove it is by some martingale to observe that this object is a martingale. And once it is a martingale, essentially we can show these two things. And it's a martingale with every time where someone plays with the bounded jump if you do something unexpected. Okay, so by the martingale convergence theorem, essentially it follows. The second part is, I think, the technically most interesting part, is how to show that this dynamic converges. So let me give it an intuition to it. So fix some, let's say that we talk about some small epsilon. So the typical, and delta equals 0, which is the epsilon DeGroot dynamic without extremization. So the typical behavior of this dynamic will be that in the short run, they will reach approximate consensus on this belief. Okay? What will happen in this dynamic after this short run time, that it very slowly will either go to 0 or go to 1. But let's forget about the fact that it will go either to 0 or to 1. We just interested in observing that in the short run, this will be its behavior. And if we choose delta to be sufficiently small, then once players will be almost in a consensus, then they can, essentially this notion of extremization will start to play a role. Okay, we choose delta to be sufficiently small in order that it will not ruin this property, that players reach a consensus on something good. Okay? And thereafter, yeah, what I just said, that if the short run consensus is on something above the diagonal, then it will lead the dynamic to 1. And if it's below the diagonal, it will lead the consensus on 0. Okay? The technical tool to do it formally, not intuitively, but formally, is stochastic approximation. Okay? And this is the main tool that we use for the proof. Okay, thank you. Yeah. Yes. No. For sufficiently small, no. There exist some thresholds that for yes. Yeah. Sorry. Okay, so what we saw here is probability matching, which is a probability matching is a phenomena that people see in the lab, at least, that if you believe that some event will happen with probability, let's say 1/10, and they ask you to bet, then 1/10 of the times you will bet on the, not you. Humans in the lab will bet on this rare event. So this is probability matching. And, yeah. So let me think. It's a good question. Okay. Let's take it on. I will have an answer in a few minutes. I hope so. Yeah. Yes, yes. So about the rate of convergence, indeed, yes, as you take epsilon to be smaller, the rate of convergence of this thing becomes slower and slower. And the delta, as delta becomes closer to the diagonal, again, it becomes slower. So in terms of rate of convergence, the rate of convergence of this dynamic is not so good because we need to pick low values of epsilon.